The percent ionization or dissociation of an acid. The percent ionization or dissociation of an acid, either word is fine, ionization or dissociation, that is equal to the equilibrium H plus ion concentration divided by the initial concentration of the acid, and then times 100 to make it a percent. So the percent ionization of this 0.1 molar HCN solution is going to be equal to the equilibrium H plus value, so 7.0 times 10 to the negative 6, divided by the initial concentration, 0.1, and then times 100 to make it a percent. This is a very weak acid. Only 0.007% of the molecules dissociate. Okay, so we've done percent ionization. Again, we're doing a little bit of wrap up here. But what we haven't done, so here's our percent ionization or dissociation formula, right? Remember, it's the equilibrium H plus ion concentration divided by the initial concentration of the acid times 100. What we haven't done is one of these. So here's a variation of a percent dissociation formula. I'm giving you the percent dissociation. I'm giving you the initial concentration of the acid. And I actually want to know what the pH is. So go ahead and then the Ka. Okay, but first, why don't you give me the pH of lactic acid if a 0.1 molar lactic acid solution has a 3.7% dissociation or ionization? What would the pH of that solution be? Think your way through it. If you get stuck, write the formula for percent ionization, right? Try to see what you have, what you don't have. You can figure this out. You got this, folks. All right, so let's do this. Here we go. Hopefully you had some time to think about it. Key to getting this problem right, I think, is writing the formula for percent ionization. So the formula for percent ionization is the equilibrium H plus ion concentration divided by the initial concentration of the acid times 100. And we're going to solve for that, right? That's what we don't have. And then once you have the equilibrium H plus ion concentration, pH is the negative log of that, and you get the pH really easily, right? So here we go. 3.7 equals x over 0.100 times 100. Divide by 100, multiply by 0.1, blah, 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 right? So divide by 100, and then multiply by 0.1. And we get x equals 0.0037. And now pH equals the negative log of that. I'm going to go with 2 sig figs. Since this problem had a percent in it, I'm not going to grade sig figs on that, but I'm going to go 2 places past the decimal. That 0.1 molar lactic acid solution should have a theoretical pH 2.43. You stick a temp, or if you have a temp probe, you stick a pH probe in there, should have a pH of 2.43. Now, the extension of this problem, it wanted the Ka. Okay, so if we go back, we can grab that formula of lactic acid because it didn't matter up until now. So it's HC3H5O3, right? Let's see if my short-term memory can do this. It's HC3H5O3. So now what we can do is we can write a dissociation equation, write a mass action expression, okay, make a ice table, okay, and solve for the Ka. Okay, so we're going to do a dissociation equation. We are going to make a mass action expression. Nope. H5. What am I doing? Cool. And let me write down that equilibrium, the equilibrium H plus ion concentration 0.0037. Now what we need to do is make an ice table. Okay, and then plug that junk into here, and we can get that Ka value for lactic acid. It was a 0.1 molar lactic acid solution. That goes down by X. These guys go up by X. That's 0.100 minus X. That's X, and that's X. And here's the nice thing now. Because we solved for that equilibrium H plus ion concentration, we know what X is. It's 0.0037. So now we can get the equilibrium lactic acid concentration as 0.0963. And now we can plug all this into the mass action expression, solve for that Ka value. So you're hopefully kind of getting the theme here, right? All of these problems, right? You are writing a balanced dissociation equation. You're making a mass action expression, you're making an ice table, right? It's like, when in doubt, start doing that stuff, right? Like that's the ticket, and at least there's some partial credit, right? Name of the game, it's the meaning of life, right? Get as much partial credit as you can. .42 times 10 to the negative fourth. That's what we get for that acid dissociation constant for lactic acid. So it's a weak acid, but in terms of weak acids, it's not like super weak, right? Times 10 to the negative fourth isn't as weak as like times 10 negative eighth or something. So there you go, folks.